So without further ado, if we may start with our first talk is a merged talk. And first we will hear from Omri Shmueli, and then we will hear from Shih-Han.
Okay, thank you, Anne. Welcome to this QIP talk. As Anne said, the first part is post-quantum zero knowledge in constant rounds, which is joint work with Nir Bitansky. So this work considers a zero knowledge protocol. So let's first briefly define what it means. So the setting is that we have an NP language L, we have an instance in the language X, and the protocol consists of two interactive algorithms, the prover and the verifier, where the prover tries to prove to the verifier that the instance is in the language, and the verifier decides to accept or reject in the end. So more precisely, we are going to consider zero knowledge protocols that are secure against quantum attacks. So let's formally define what it means. For the honest parties, the honest prover algorithm and the honest verifier, they are both classical and polynomial time algorithms. And the completeness guarantees that if the instance is in the language, the verifier is always going to accept, given the fact that the algorithms are ran honestly. The soundness intuitively says that the verifier cannot be tricked, which means that if the instance is not in the language, then any quantum polynomial prover, which arbitrarily deviates from the protocol, cannot convince the verifier of rejecting, the verifier cannot convince it to accept, the verifier will reject with probability exponentially close to 1. The zero knowledge intuitively says that the verifier learns nothing from the interaction with the honest prover. This is formally captured by the following definition. Consider the process where the quantum polynomial time malicious verifier interacts with the classical prover, and we denote by psi the output of the verifier at the end of the interaction. Without a loss of generality, this can contain everything that the verifier learned during the interaction. And we are guaranteed by the zero knowledge that there is some quantum polynomial time algorithm, which we call the simulator, so that for every quantum polynomial time verifier, this output of the verifier is going to be simulatable by the simulator. Now, importantly, the simulator does not interact with the prover. It only has access to the code of the verifier and the instance. Okay. So what we knew before this work on the round complexity of zero knowledge and compared to the security. So for since the end of the 80s, for more than 30 years, we know how to do classical zero knowledge in constant rounds. And since the beginning of the early 2000s, we know how to do quantum zero knowledge for NP in polynomially many rounds. This is the seminal work of John Waters. We did not know how to do quantum zero knowledge in constant rounds. And note that we are aiming for classical honest parties, but this question was open, even if we let the prover and verifier be quantum with the quantum communication line between them. Okay, so the results are that if we assume the existence of quantum fully homomorphic encryption and the quantum hardness of LWE, you can construct a constant round quantum zero knowledge argument for NP. You can also construct what's called a quantumly extractable classical commitment, which we will define in a bit. And as a corollary of these two theorems, along with previous work on zero knowledge for QMA by Broadbent, G, Song, and Waters, we show how to construct a constant round quantum zero knowledge quantum argument where the honest parties are quantum for QMA. But in this short talk, we are going to focus on the NP part. So how to construct a constant round quantum secure zero knowledge protocol for NP? So very roughly, usually constructing a zero knowledge protocol can come down to constructing a commitment scheme. More precisely for our causes, if you want to construct a constant round protocol, zero knowledge protocol for NP, an approach by Rosen shows that you can, it's enough to construct an extractable commitment. It can be easily shown that this approach by Rosen can be extended to the quantum setting, which means that if we have a quantumly extractable commitment, which we define in a bit, you can construct a quantum constant round zero knowledge for NP. So this is the hard part to construct. Going from here to here is very easy. So this is going to be our goal, how to construct a quantumly extractable classical commitment. So what exactly is this cryptographic functionality? These are two interactive algorithms, the receiver and the sender. The sender wants to commit to some classical message M, so they interact a constant number of messages. And at the end, the commitment, we can think of it as the entire transcript. We have the usual perfect binding, which means that the sender, after the interaction ends, the sender can open to at most one message. The hiding says that M is hidden until the sender decides to open the commitment. And the extractability says the following thing. So we're going to consider the process that the honest receiver interacts with a quantum polynomial time sender, malicious sender. They interact, they have a commitment, and the sender has an output at the end of the interaction. And also M is the value under the commitment, the value that the sender committed to. And you are guaranteed that there is some quantum polynomial time extractor such that for every quantum polynomial time malicious sender, all of these three elements are going to be efficiently simulatable by this extractor. And we call this extractable commitment because the extractor manages to simulate the state of the sender, but also extract the committed message. Okay, so it will be instructive because we won't have enough time to go into the techniques. It will be instructive to understand why the previous techniques in the how to do a classical extraction, why these don't work when we want to extract from a quantum computer. So recall that the extractor has the code of the sender, and it uses this code of the sender to simulate an interaction. And the sender is an interactive algorithm, so it has some inner states, some inner memory that it uses during the interaction and maintains this memory space during the interaction with the other side. It keeps all of its secrets in this memory space, and we call it the inner state. So at some point in this simulated interaction, the extractor is going to take a snapshot of this memory state, of the inner state, and put it on the side. Now it's going to continue the interaction in some arbitrary way. It's going to send alpha in order to obtain some sensitive information beta. This is in a very high level, how we do this extraction. Now, given the fact that it has beta 1 and 2, it has the copy of S1 from before, it can effectively rewind. This is called rewinding, effectively rewind the sender to this spot, but crucially now it knows beta, and it's going to continue the interaction in a new way based on the fact that it has beta. And this continuation based on knowing beta allows the extractor to extract even more sensitive information, consequently leading to knowing the committed message M. Okay, so the previous extraction strategy fails when the sender is quantum, and it can be easily seen well. So we cannot copy this. If the sender is a quantum computer, its memory space is a quantum state in particular, and we cannot, by the no-cloning theorem, we cannot copy this inner state here. The extractor can try to continue the interaction in some arbitrary way, but the point is that this output register that contains beta and this inner memory space that the sender keeps to itself, these two registers are entangled. And when the extractor measures this register, it's going to destroy the information that was here. And we cannot go back from here to here. And we also did not take a snapshot, so we don't know how to do this rewinding technique when the sender is a quantum algorithm. Okay, so we saw one example of one technique that seemed to not work. It is natural to ask what about other extraction techniques. The point is that all known techniques either use cloning of the inner state of the sender or use tools not known for quantum computations. This work aims to ask, how can we extract from the sender without cloning whatsoever. And we will not have time to look at the technique, but in a very, very small nutshell. So this is the small nutshell. So we want to extract in a straight line. We want the extractor to do the simulated interaction in a one way without rewind. Also, the rewinding technique, the traditional one that we just seen, it uses the sender, it treats the sender as an oracle. It does not use the fact that it has the actual code of the sender. This is called black box extraction. And if we could do both, which means if we could extract in a straight line and in a black box way, you can prove that the commitment will not be hiding. So in our work, what we show is that one thing the extractor has that the malicious receiver does not have is the code of the sender. And you can use the code of the sender along with quantum homomorphic encryption in order to extract. So let's just recall what is quantum homomorphic encryption. This is an encryption scheme where you can encrypt an input. Then you can take this encryption in a quantum circuit and evaluate it to get an evaluated ciphertext. And then you take the evaluated ciphertext and decrypt it, and you get the state that you should have gotten if you computed on the if you computed it without encrypting before. So the trick is that you can homomorphically evaluate the quantum algorithm of the sender, and by doing this, you can extract. And for the full talk, you can look at it in this link in YouTube. And thank you. And this is the end of the first part. And now Shih-Han will talk about non-interactive zero-knowledge protocols for QMA.
Hi, so the second part of the talk is about non-interactive zero-knowledge protocols for QMA. This is a merge of two papers. One is by Andrea Coladangelo, Thomas Vidick, and Tina Zhang. The other is a joint work with Gorjan Alagic, Andrew Charles, and Alex Grilo. So Omri just told us about zero-knowledge protocol for NP. An interesting question is that can we make the structure of the protocol really simple? Maybe we can ask is non-interactive zero-knowledge for NP even possible? So here saying that the protocol is non-interactive means that there is only one message from the prover to the verifier. And then after receiving the message, the verifier outputs accept or reject. So by Gorjan and Oren in 1994, the answer is no, because such a protocol only exists for BPP languages. So an interesting relaxation is to allow a set of phase established between the prover and the verifier before the verification starts. So there's a long list of classical work about this. Here I just want to mention that in the common reference tree model, there is an instantiation based on hardness of learning with errors by Piker and Shih-Han in 2019. So here, a common reference string model means that there is a common string shared between the verifier and the prover. And the string is sampled from a public distribution. If the distribution is uniform, then it's also called a common random string model. So to extend the problem to the quantum settings, Omri just told us about zero-knowledge protocol for NP against quantum adversaries. So this part, I'm going to talk about a different setting. Where can we construct zero-knowledge protocols for quantum classes such as QMA which is a quantum analog of NP. So depending on whether the protocol is non-interactive or not, and whether the prover is required to process quantum information, there are different results. So the first result is by Broadbent, G, Song, and Waltros in 2016, which is the first protocol for zero-knowledge protocol for QMA. And Broadbent and Grilo gave a protocol based on quantum QMA hardness of a consistency of local density matrices. And as a corollary, Omri's results also imply a constant round zero-knowledge protocol for QMA. With a purely classical verifier, Vidick and Zhang in 2019 gave an interactive protocol for QMA, which uses idea from Broadbent, G, Song, and Waltros and the MADA protocol. So it leaves open whether you can have a purely classical verifier and a non-interactive zero-knowledge for QMA. So in this talk, I'm going to talk about two protocols where the only message from the prover to the verifier is classical. In the first protocol, I'm going to talk about NIZK for QMA with a quantum preprocessing phase. And in the second protocol, I'm going to talk about NIZK for QMA with a purely classical verifier. And the security holds in a quantum accessible in the Oracle model. So the first part is NIZK for QMA with quantum preprocessing. So consider the following zero-knowledge protocol for QMA, which is simplified. So on receiving which verifies the local Clifford Hamiltonian problem, which is also QMA complete. On receiving the instance and the witness state, the prover encrypts the witness state with quantum one-time pad, and then sends over the encrypted states together with a commitment to the keys. So the prover is not allowed to change a value afterwards. And after receiving the encrypted states, the verifier samples a local term and measure the quantum state with a local Hamiltonian, which can be realized with a Clifford circuit followed by a cylinder basis measurement. The verifier sends over its choice of the term and the measurement outcome to the prover. The prover could have revealed the key values so to get accepted, but that breaks the zero-knowledge property. So instead, the prover sends over a NIZK proof for the NP statement, which says that there exists a set of keys such that the verifier accepts. The protocol is not, it takes 3 messages because the verifier has to perform measurement and sends over the outcome on the encrypted witness state. So a question is that how does a verifier perform the measurement before receiving the instance or receiving the witness state? Yes. This seems a challenging question to ask, but it turns out that we can do that by using quantum teleportation. So remember one way the prover could send encrypted witness state to the verifier is by teleportation. So initially the prover and the verifier share EPR pairs. The prover performs Bayes measurement on half of the EPR pairs and the witness state, followed by Clifford measurement done by the verifier. But the actions of the prover and the verifier commute. So the verifier could do the Clifford measurement before the prover performs the Bayes measurement. So putting things together in an instance independent preprocessing, the prover prepares EPR pairs, measures one half with a Clifford Hamiltonian, and then sends encryption of the outcome and the other half to the prover. In the verification phase, the prover teleports a quantum state by performing Bell measurements and then sends a NIZK proof for the MP statement. So I just simplified the protocol a bit. So in the full version of the protocol, we also use a classical circuit private fully homomorphic encryption. And the protocol is computation is sound and computation is zero knowledge. Because there is an instantiation from LWE for this fully homomorphic encryption, so the whole setup is based on the hardness of learning errors. So the second part of the talk is about NIZK for QMA with a purely classical verifier. So recall the MADEP protocol for QMA, which verifies XZ Hamiltonian problem, which is also QMA complete. So initially, the verifier and the prover receive a secret key and a public key, which are associated with a key pair. On receiving the instance and the witness state, the prover interprets the public key with as a function and query the function on the witness state in superposition. And then the prover measures image register and sends over the outcome Y to the verifier. After receiving the string, the verifier sending a random challenge requesting a standard basis measurement or hardness basis measurement. And then the prover measures the residual quantum states and then sends over the measurement outcome to the verifier. But the protocol is not zero knowledge because we cannot present a simulator which simulates in particular this the distribution over Y and the measurement outcome U without having access to the prover or the witness state. So then we can consider the following zero knowledge variant, which uses a similar idea as the first protocol. So on receiving the instance of the witness state, the prover encrypts the witness state with a quantum one-time pad and queries a function on the encrypted quantum state in superposition. The prover sends over the measurement outcome Y along together with a commitment to the key values. So the prover is not allowed to change the value afterwards. So then the verifier sends over during the challenge. The prover could have revealed its key value and the measurement outcome to get accepted. But again, this breaks the zero knowledge property. So instead, the prover sends over a NIZK proof for the MP statement, which says that there exists a set of keys and measurement outcomes such that the verifier accepts. So to apply, to make the protocol non-interactive, we apply a wrong reduction technique called Fisher-Shamir transformation. But before doing that, we need to reduce the soundness error by applying parallel repetition. So a parallel repetition is established in two steps. The first is by this adaptive orthogonality property, which I'm not going to explain this in this talk. The soundness error decreases exponentially in the number of copies. And then by the soundness of a MADEP protocol, we can show that the adaptive orthogonality property holds with this protocol. And then because we have a protocol that the soundness error is super polynomially small, then we can apply Fisher-Shamir transformation, which is transformation that turns free message public coin protocol into a non-interactive one. So in the quantum random oracle model, Fisher-Shamir preserves the soundness and zero knowledge. Again, I just simplified our protocol for exposition. So in the full version of the protocol, we also require, we also use classical circuit private fully homomorphic encryption. So the whole setup is based on hardness of learning errors and the quantum random oracle model. So in summary, I just mentioned two NIZK protocols for QMA. One is with a quantum preprocessing step. The other is in the quantum random oracle model with a purely classical preprocessing. So for open questions, can we present classical NIZK for QMA with simpler setups? And whether it's possible to give an instantiation of the future mirror transform that I just mentioned. So thanks. That gives a talk.
Thank you very much. We just have a couple minutes for questions. And just a reminder that the questions are being dealt with over in the Slack channel. So there's a question that came for the first part of the talk. Oh yes, thank you very much. Virtual applause for everybody. Question that came to the first part of the talk was for Omri, and the question is from Ifke Dulek. The last part went a bit too quickly for me. Why was the FHE, fully homomorphic encryption, useful, and who holds the key here? Who holds the secret key?
Right. Yeah, it was. I cannot even say that it was in a nutshell. So. The one who holds the key, so how is it useful? So what's going to happen is that the sender is going to take a random string, send an FPK encryption of this string to the other side. And then it's going to tell to the other side something along the lines of, if you're going to send to me an encryption of another random string, then you're going to be able to extract the secret. Okay, let me, just a second. Okay, no, sorry. It uses a different encryption. It takes this secret string S that the sender sent to the other side. And if it finds another encryption of the same string, but not under the same classical secret key, then you can extract this message from the sender. I think, yeah, I don't know how to like explain it in a super succinct way, but so yeah.
Thank you. Just a reminder that there will be a roundtable discussion after the session in about an hour that people can continue the discussions and meet with the speakers. So we'll take a short pause and start with the next speaker